Welcome back to the hyperbolic coding chamber. We are back once again. As you can see, I'm donning the national holiday robe. So it is the land of December, and yes. So we're back once again. Also, the advent of code has started. So it'd be interesting to poll anyone who watches to see, do you do the advent of code? I'm thinking of trying it for the first time, but I'm not exactly certain. I skimmed through the first problem. It seems pretty different than what I'm used to, so I don't know if I'm actually going to do it. But it'd be interesting. I'd be interested to hear like veteran advent of coders. How is that? How does that work? Because there's not a thing you can type into like LeetCode, so I'm not sure what exactly the angle is. I guess you just solve it locally and put the answer in, but I'd be interested to see or hear of other people's experience with it to know if it's something that is worth trying. But it could be cool to do something festive, but I'm not exactly certain how we'll fit it into all the LeetCode and stuff. So we shall see. There are many hours of LeetCode to extract, so too many hours of advent of code, we end up losing out on LeetCode. Always the journey is to learn though. But when I started this, I thought that by the time we got to day 168, or I thought by the time the advent of code started, that it would be remedial. So things have changed since then. So after doing 100, almost 200, I don't even know how many problems now. Most of them are easy, 216 problems. I'm sure we could do okay in the advent of code, but I just thought I'd be much further along. But maybe that's part of the secret sauce. So yeah, so maybe that's part of the secret sauce. I remember, I think it was Will Smith or someone who was saying this, but like they were saying that like basically we pretty much thrive, and I find this in myself, based on the stories we tell ourselves. So I think when I started this, I told myself the story that by 168 I would be a problem. By the time the advent of code started, we would be a problem, and we are not a problem. It turns out LeetCode is truly the problem. So by day 365, though, and maybe this is copium, by day 365, advent of code will be remedial. So I'm going to put my hopes on 165 days from now that we will be unstoppable. If we could get if we get up to like 2 hours of LC a day, oh man, that would be a dream. That would mean that in 165, this is the issue though. In 165 days, we spend an hour doing LeetCode every day. That'd be 165 hours. But if we did 2 hours a day, it would literally be the progress of 2 years in the progress of a year. It would double our progress basically. So that is unfortunate. So I don't know how to get that in there, but I guess the first thing we should aim for is making sure we can do a bare minimum an hour a day. So we shall see. But yeah, I'd be interested to know how that goes. Also, how your LeetCode journey is going, if it is going well. So I'm gonna pop over to the comments, and it looks like we have some general daily carnage, but from the Ice Cream Man 1337 with the tennis ball profile picture. The person reading this comment is a silly goose, and I hope they have a nice day. It feels strong, man. So we have 3 thumbs up, and we have Sean Turner looking quite spiffy with a classic no you. So great words of wisdom. And so we have no choice but to accept our fate and resolve to spend another hour in the chamber where suffering is immortalized and accelerated. So that being the case, it's time to lock in for another hour of LeetCode. It's time to zoom. Also, that being said, people probably clicked off by now. Also, I checked the graphs, and the engagement drops off. The engagement drops off as soon as I say I'm gonna jump into the LeetCode. In fact, I think I looked a little bit closer. As soon as I say let's jump, the engagement drops off a cliff. So most people have probably already clicked off by now, but yeah, it was just funny to note that as well. So we're gonna do an hour. I'm gonna jump into it, and yes. So hopefully we can jump through quite a few problems today. And Yeah, we have problem called maximum 69 number. I'm not sure if we already solved this. Oh, we did, and it seemed to be okay. I mean, it would be linear time, linear space. That's mostly because JavaScript doesn't have mutable strings. So if we had a mutable string, this would be constant space. But I think we'll take it. I'll pop over to the solution just to see if there's anything. Yeah, all of these are O of L. So keep moving. Given an array nums, return true if the array was originally sorted. Given an array of numbers, you want to return true if the array was originally sorted in ascending, in non-decreasing order. How do we know if the array was already sorted? Oh, then rotated some number of positions, including 0. I think we could do this. I think all you'd really have to do is iterate through it once to find the boundary where you're going from 5, you're going from a large number to a small number, which would indicate a rotation. And if we can't find that, we'll just assume index 0. And then what we'll do is actually, if we can't find a number where a boundary where we're going from a large number to a small number, we'll just return false, because the array, then rotate it a number of positions, otherwise return false. So if it's already in sorted order, you return true. So I think we can do this. So basically have to find boundary, then treat it like a circular array. So here we're trying to find our boundary index, which we'll set equal to -1. And then we'll say if boundary still equals -1 after we try to find it, right, we'll return true. It's already sorted. Right? To find the boundary, all we have to do is iterate through, right? And we'll subtract nums.length -1. And this is just so that we're going to be checking one number forward. We don't want to go out of bounds. We'll say if num sub I, right, is greater than nums sub I plus 1, then we'll say boundary is equal to I. And for these starting cases, we should fail the first two cases. If we return true, we're going to, I guess we'll only fail the second case. And that's okay. Now that we're starting at the boundary, all we need to do is we'll have another pointer which we'll call P1, which depending on the boundary, right, if the boundary is actually we should be safe to add 1 to it. So the P1 will just be boundary plus 1. And what we're going to say is while nums while P1 does not equal boundary, because that's when we'll stop, right, while P1 does not equal boundary, right, and we're just going to check, right, that the current P1, right, and if we increment it 1 forward, are we still less than that element? And as soon as that's false, so if num sub P1 is ever greater than, we'll have we'll say next position, right, which will be equal to boundary, boundary mod, and we want to do just some wraparound here. If boundary is equal to nums dot length, right, then we want to wrap it around to 0. Otherwise, we can just do boundary. We can just do P1 plus 1. What we really mean is P1 equals nums dot length. And we'll say num sub next position, right? If num sub P1 is greater than it, we'll return false. And then we can actually just say P1 equals next position. So if we look at this thoroughly, the boundary we should get should be index 1, right? So we won't return true, right? We'll let P1, and this actually might be easier to read if we just set this equal to P2. P1 is going to be equal to boundary plus 1, which is going to be equal to index 2, right? Now we're going to ask if num sub P1, which is 3, right? Well, first we have to calculate what P2 is. P1 is equal to index 2, right? 0, 1, 2. Right? And so since P1 is not equal to nums.length minus 1, which means we're at the last possible index, right? We're just going to do P1 plus 1. So our next index is just going to be 4. Is 3 greater than 4? No. So P1 equals P2, right? So now we go to 4. We go back up. P1 does not equal boundary, so we keep going. P2 is going to be equal to, well, now P1 is equal to nums.length minus 1, which is 3, index 3. So we're going to set it P2 equal to 0. And now say it's 4 greater than 2. Yes, so we're going to return false. So that's pretty cool. And we'll take it. There should be linear time with where n is the number of elements in the array and constant space. Additionally, I actually just realized I never finished reading the whole problem. There may be duplicates in the original array. I think we're actually evolving. I didn't even read the whole problem and we solved it. Oh, it's in an array B of the same length. Not really sure what this person was doing. So this person iterates over the whole array. Right, and they count up, okay. Right. Okay. So they count how many spots are in the correct place that are sorted correctly. That should give you I n minus 1 since we're checking one forward. And if it's rotated, then you'll stop halfway through. So they do another loop and they go until the end. Now, if you add those together, it should still be equal to n minus 1. And num sub n minus 1 with an edge case. That's interesting. Oh, this one's clever. 5, 6, 6, 7, 10. He counts how many boundaries are allowed to exist. So how many times a number can be greater than its neighbor. Right. And you can add an extra check for the wraparound. That's really clever. That is really clever. So we'll go to the next problem. You have a lot of dislikes on this one. You have a set of integers s. You have a set of integers which originally contains all the numbers from 1 to n. Unfortunately, due to some error, one of the numbers in S got duplicated to another number in the set, which results in a repetition of one number and loss of another number. You are given an integer array nums representing the data status of this set. After the error. Find a number that occurs twice and the number that is missing and return them in the form of an array. I think we can figure this out. If the set of numbers should be contained should be from 1 to n, one number was duplicated. Since a number was duplicated, but another number was lost. Well, if we just figured out the duplicated number, then you could just do Gauss. This doesn't seem too bad. You find duplicate. All right, and you subtract it from the sum, and then you should be able to subtract the actual sum. Find duplicate, subtract duplicate from sum, subtract duplicate from actual. Oh no, we actually can't know that. They're not all the numbers from 1 to n. Actually, it does contain all the numbers from 1 to n. Okay, so we can subtract the duplicate from the actual sum with Gauss. actual sum, and then we'll subtract that from Gauss to get the final number. Are we guaranteed this always exists in the array? The length is always at least 2. I guess we can assume that it always exists. We could use a set. We'll do for const num of nums. If the set does not have the number, then we'll do set.add num. Else, dup equals num, because that's the duplicate. And then we'll break. Actually, we'll keep going. And we'll let actual sum start at 0. And we'll just do actual sum plus equals num. And we should be able to return dup and n, or nums.length, it's n times nums.length plus 1 over 2. Now if we take Gauss, and then we take the actual sum, subtract the duplicate, I think we should get the correct answer here. Wow, we're getting lucky today, it seems. So the set, this would be linear time over it. The set would take linear space, so linear time, linear space. Is there a follow-up? Could you do this in constant space? I think you could do this in constant space because you could just sort the numbers in the array and then the two duplicates would be right next to each other. And then you could do what we just did here, but the time complexity would change to n log n. I guess you could, wait. Nums, they always use this trick, math.ab sub n minus 1, to whenever we have a data over a set that can be contained in an array, you can use the same array to store information. So they know the whichever one is negative, that's what the dup is. That's pretty cool. That is pretty cool. It looks like we're getting lucky today. So let's see if there's any more we can do. A lot of dislikes on this one. Given two strings S and goal. Return true if you can swap two letters in S so the result is equal to goal. Otherwise return false. Oh, it's not that simple. Hmm. Mm. Given two strings S and goal, return true if you can swap two letters in S so the result is equal to goal. Otherwise, return false. Return true if you can swap two letters in S so the result is equal to goal. Oh, it's only two letters. You can swap two letters. I think I was way overthinking this now. I'm thinking about it. Two letters. We can add what we said before. If S equals goal, we can return true. No, we can't. The difference. What if we just loaded both strings into a set? Well, one question would be, when can we actually swap? For example, if we get A, B, C, D, E, and A, C, B, D, how many characters in the wrong place here? 3 are in the wrong place. So you need more than one swap. If you put E back here, then only 2 are in the wrong place. And you could swap them. Now, if we do swap them, does it equal goal? How many cars differ from goal? To check if swap equal goal. So here we check A and B. 0 cars differ. If they're equal to each other, the answer is always false. It should help us with examples 2 and 3, except for 1. Issue is, if they didn't give me the examples, I would have never caught them. That's pretty bad. Second one is S is equal to AB. So I think we should be able to swap these. And return if r.join equals goal. If you have no characters different, then maybe we'll just return. I think we should default to false. If you can swap two characters, now what if there's only one character that's different? There's only one character that's different, then you'd return false because you can't swap any other characters with it. No characters are different, then we have these two cases appear. Now, if they're the same and set.size does not equal 1, they're the same, but set.size does not equal 1, means there's the bunch of different characters. If there's a bunch of different characters, maybe that's okay. We'll have to check. The issue with this algorithm is it assumes that if two strings are the same, then they're fine. It only works when there's different strings. I think we need an algorithm that puts swapping at the forefront. So, how can we solve this? If we can swap two letters in S so the result is equal to goal. Swapping letters is defined as taking two. We just have to be able to swap two letters. My issue with is the last two, that final case. If they're the same, we go to our previous submission, or can we restore it? To our previous one, we should fill out that last case. And instead of trying a different solution, what if we just go through it and we say else if S is equal to goal, and set.size mod 2 equals 0 will return true, because it would mean that the characters are the same and there are an even number of different characters we can use. If that's the case, we can guarantee we can swap at least one of them. Oh. Maybe we should run this one first. Set.size does not equal 1 is way too large. S.length is greater than 2. If I had test case AB doesn't make any sense to me. I'm trying to pull at some structural property. But I think the way I'm pulling at it ignores something. I think we're ignoring a dimension of the problem. If the strings are the same, and we have 4 different characters, then we have S is equal to A, goal is equal to A. We'll add one more case. We're forgetting a lot of semicolons. If S dot length equals 1, return false. This problem is kind of miserable. I have to be honest. This is a miserable problem. I can't figure out what exactly about these problems is miserable, though. I wonder if you can just do this. So you can't. Something is miserable about this problem. It looks like the time would be linear time, though, even though we're going over it quite a few times. With linear space in the worst case in the set if every character is unique. But actually, if it's just lowercase, S and Go consists of lowercase letters, then set would actually be constant space because we'd always be limited to 26 keys. But this diff array we do have to check how many different characters there are, and it could be that S and Go differ completely, so you'd still end up with linear space. Even their solution ends up looking very hacky. even yeah, something about the way the problems are solved, it ends up being very specific. I guess there's no general algorithmic pattern you have to solve here. It seems more like putting together a laundry list of edge cases. Given an array of distinct integers, find all pairs of elements with the minimum absolute difference of any two elements. Turn the list of pairs in ascending order with respect to pairs. Each pair A, B follows A, B are from R. A is less than B. B minus A is equal to the minimum absolute difference of any two elements in R. So maybe the question is asking, given an array of distinct numbers, find the minimum absolute difference that exists, and then find all other pairs that give you that same minimum absolute difference. I think you could do this in two passes. One pass to find the minimum absolute difference, then another pass to collect the other pairs. And if we sort the input, the output should also be sorted. And we should just be able to check the nearby element. So let's try that. Say r dot sort a comma b, a minus b. We'll call this the mads. Minimum absolute difference is equal to infinity. We'll say for let I is equal to 0, I is less than r dot length minus 1, I plus plus, and we'll say mads is equal to the math.min of mads and r sub I, the math.absolute value of r sub I minus r sub I plus 1. So the minimum absolute difference is 1, then it should be 2, and then it should be 4. Then we should have pairs. You only have a minute left. We should be able to return if we copy this same loop. Why do we have a parenthesis issue? we should just have to say pairs dot push r sub I and then r sub I plus 1. This might not give us all of them actually though, because you could have something like negative 14 and then something like positive 20. But then even if you subtract them, you wouldn't get 4. Nice. So we have just enough time left. So we'll stop there. And it says this is pretty slow, but if we do n log n, it should be n log n. And if I don't know if we count output, but it should just be n log n with constant space. Why is there no constant space solution? I don't understand. We're also not reading. Oh. Interesting. The JavaScript, the space complexity of sort is log of n. So that's interesting. So that is actually interesting. So I guess I understand now. We're going to come back and read this counting sort of approach tomorrow. So that sounds pretty useful, but we'll stop there today.